Welcome back. So this is video 2. You should have started with watching ionic compound video, and that's not at all what I named it. I named it all about ionic compounds. So this video will be all about covalent compounds, which I think is a little bit easier than our ionic counterpart here. And let's just get started. In covalent bonds, two atoms are going to share valence electrons to obtain their full octet. So what we saw in ionic was one atom just really doesn't want its valence electron or electrons, and another atom does. So it's just like a donation situation. Covalent bonds are different. There is no donating happening. There's sharing, and as you'll see in a bit, there's some unequal sharing, but sharing nonetheless. Covalently bonded compounds, these are called molecules, include two or more nonmetals just bonded together, and this is where we see an actual physical bond because they're sharing those valence electrons. You know, they're covalent. Get it? We're not trying to confuse you. The atoms have a smaller difference in electronegativity than what we see in ionic compounds. So with ionic compounds, we see a difference that's larger than 1.7. In covalent compounds, we see anywhere from 0 to 1.7. And that's an approximation. You'll see different cutoffs in different sources, but our textbook calls it at 1.7. When electrons are shared evenly, that's a difference in electronegativity between 0 and 0.5. The covalent bond is called nonpolar. And when electrons are shared unevenly, that means one is hogging the electrons a little bit more, but it's just sharing a little bit. The covalent bond is called polar, and the difference in electronegativity we see goes between 0.5 and 1.7. We'll work more with that next week when we start talking about molecular structure. We'll deal more with electronegativity. So I have these lovely little visuals here just to show what we mean by covalent. In this example up here, you see each chlorine atom has 7 electrons in its valence shell, and we wouldn't see the same exchange where maybe this chlorine just donated to that one, then this chlorine would be happy with 8 valence electrons, but this one would be more unstable with only 6. So that's just not going to happen. What we see is that they decide to share. So now this chlorine has 8 and this chlorine has 8, but they are sharing, and that sharing of electrons is a bond. And what we see in every bond is that there are 2 electrons in it. So yep, one bond is 2 electrons. And here we can see the difference in polar and nonpolar. So this is what we mean by uneven sharing. Get my little handy dandy pen here. But let me think of a polar covalent bond. So let's say we have hydrochloric acid, or HCl. And this is our bond. So chlorine has 1, 2, 3, 4, 5, 6, 7. Hydrogen has 1. They're going to share here. So now both are happy in this sharing. But chlorine is way more electronegative. It's going to attract electrons better than hydrogen. So even though they're sharing, chlorine is sharing unevenly. It's like if you have older siblings, they're sharing, but they're not really sharing evenly. It's like, hey, I cut this piece of cake in half. No, you didn't. You're hogging it. That's chlorine. Chlorine is hogging it. Okay. In nonpolar covalent bonding, we see not that situation. So let's say we have 2 hydrogens. Remember, hydrogens are happy when they have 2 valence electrons instead of 8 because they're in that first shell. But these 2 are going to share electrons here. Now they're happy. And because they have the same exact electronegativity and they have the same strength, they are going to share evenly, like we see in this much better picture. And then in an ionic bond, we know the difference in electronegativity is so big that there's no sharing at all. So one atom is just going to take away electrons from the other, and the other one is generally okay with that. And that's what we saw in ionic bonding in the last video. So yep, that's our difference here. And then here's just another picture over here. And we have oxygen bonding with 2 hydrogens to form water. You see this hydrogen is going to share this electron, and this oxygen will share that electron, and this is our bond here. That's a bond, and that's a bond. Covalently bonded. So yep, that is all. So here's some properties of covalently bonded compounds. The first one being physical and chemical properties of covalent compounds depend on the molecular shape and the intermolecular forces, which is just interactions between molecules. So depending on the shape of our molecule, that's going to change our boiling point, melting point, all that. Covalent compounds experience a weaker attraction to each other than ionic compounds. So when we're comparing to ionic, they're going to have a relatively low melting point and boiling point. So like think of water that's going to boil at 100 degrees Celsius, whereas if we're looking at salt, that's going to boil in the thousands degrees Celsius. Many molecular compounds exist as gases at room temperature for this reason. So think oxygen gas, nitrogen gas, carbon dioxide. Those are all covalently bonded molecules. And in the solid phase, covalent compounds form crystal lattices, for example, sugar. So just these crystal compounds, these are typically solid at room temperature and brittle. Non-conductors, meaning they're not conducting any electricity. Yep, those are properties. So when we're naming covalent compounds, like I was saying earlier, it is a bit easier than naming ionic compounds, in my opinion. The first element in the formula will be named first. So that's the first step. And we just use the entire element name. So just like ionic compounds where you had potassium chloride, you just say that first element name. The second element will be named using its root and adding the "ide" ending, so similar to ionic compounds. The difference here is we will use prefixes to indicate the number of atoms that each element that are present in the compound. We did not do this with ionic compounds because those charges remain consistent, so there's no point in saying how many there are. We can figure that out by knowing the charge. With covalent compounds, it's not the same situation. So these are the prefixes we'll use. We'll mainly be looking at this side of the table, even though we can get compounds that have 6 of one element or more, we'll mostly be dealing with these. So if you have one atom, we'll say mono. If you have 2 atoms of the same element, we'll say di, tri, tetra, penta, and so on. So let's look at some examples here. We have CO2, which you already know what that is. You've seen this a million times. But we start by saying the name of the first element is carbon. Now, because carbon is first, we won't say monocarbon. When it's the first element and we have no mono, we just assume there's one. And again, I swear chemists are just always looking for ways to say things shorter and condense it more. And that's what we're doing here. Then we have oxygen, which would be oxide, but we have to say how many we have. We have 2. The prefix is di, carbon dioxide. Let's try this one. Similar, but we have sulfur. We don't say monosulfur because it's the first one, but sulfur dioxide. Nitrogen, tri, because we have 3, fluoride. Carbon, tetrachloride. And we have to put a space between the two. Those are 2 different words. You might be wondering, okay, then when would we use mono? Look at H. Hold on, I have to go insert equation. Okay. H. Nope. Still no. Here we go. Love technology. H2O. That's all I wanted to type. So we have 2 hydrogens. We have to let people know. We have di, meaning 2, hydrogen. And 1 oxygen, since it's not the beginning of the formula, this is where we use mono. And we wouldn't say monoxide, we just say monoxide. Again, looking to condense everything. Yep, those are some examples for you, and there will be more practice. Now, when we're going the reverse, going from the formula to the name. And I flipped it again. I did this in the last video too. From the name to the formula is what I meant to say. From name to formula. I think it's easier to do it. There's no crisscrossing happening for covalent bonds, covalent compounds. We just look at the prefix. So I know I'm going to have 2 hydrogen, okay? H2. Monoxide, 1 oxygen. So that's just the reverse of the one we just did. I have chlorine, there's no prefix, so I'm going to have 1 chlorine. Tri, meaning I'm going to have 3 fluorines, trifluoride. I have diphosphorus, so I have 2 phosphorus. Trioxide, 3 oxygens. That's it. And I think that's a lot easier than ionic compounds. I think that's what we'll spend most of our time practicing. And then you can find more practice on page 274, questions 93 through 96. Skip the acids. We're not going to go into why did I do that? We're not going to go into naming acids. I won't ask you to memorize that, and I will just give you those. But you'll get really familiar with it, like HCl is hydrochloric acid. HF is hydrofluoric acid. HBr is hydrobromic acid. HI is hydroiodic acid. See, so I'm sure you've already got that down if you're extra bright. Okay, that's everything for covalent. I hope this one was a lot shorter, but we'll see. I'll keep my notes so you can have them. I will see y'all whenever I see you again. Bye.